Hello everyone, myself Monu from group number 322. Today our topic is chemical kinetics and catalysis. The most important function of protein is to act as enzyme. Enzymes serve as catalysis in all biological reaction. A catalyst accelerate the rate of reaction but is not consumed in overall process. The rate of chemical reaction usually greatly depend on temperature. Empirically, this dependence is expressed by Arrhenius formula for the reaction rate constant, and this is the reaction where E is the energy of activation, characterize the energy barrier that must be overcome by the system for the reaction to occur. The dependence of K on ERT follow from the Boltzmann distribution among energy level. The exponential indication indicate the fraction of molecules that possess sufficient energy for the reaction to take place. The constant K determine the reaction rate for the reversible reaction, and this is the reversible reaction. And the rate are given by A and B are concentration, where V equal to K1 and V K1A, and this O at equilibrium V equal to V, and the equilibrium constant is dependent by this. The subscript equation indicate an equilibrium concentration. The free energy difference between reaction product and reactant is equal. Here this, where H dash is the enthalpy change and the S is the entropy change. The reaction is possible only if uh, delta G is smaller less than 0. If the free energy is decreased. However, this condition is necessary but is still sufficient for the reaction to occur. The energy of activation E may be so great that the rate constant is vanishingly small and the reaction does not proceed. The catalyst serves to lower the reaction barrier. The meaning of the Arrhenius formula is disclosed in the theory to absolute reaction rate proceeds by air earrings. It is assumed that the occurrence of the reaction does not upset the Boltzmann distribution of molecule over states with different energies. For the reactions to proceed, it is necessary that an energy barrier be surmounted. Figure 6. In this figure show the profile of free energy for the certain process. Delta G is equal to G1 and G2 in the free energy difference between the essential state 1 and the final state 2. Uh, G is the free energy for the activation in the process A to 2. Let us find the number of system where which are in certain interval. Delta of the reaction coordinate this at the top of the energy barrier. The reaction rate is the number of systems that pass over the barrier per unit time. The mean velocity of the system is given by this equation. You can see we have made use of the Maxwell-Boltzmann distribution over kinetics energy mv square by 2. The reaction rate, i.e. the number of the jump over the energy barrier per unit time is given by v this equation where c is the number of system in unit volume within the interval delta. At the same time we have this equation where ca and cb are the concentration of the reaction from equation 6.6 and 6.7. It follow that this equation here k is the equilibrium constant for the passage of reactant A to an activate state. The equilibrium constant is compressed n term for partition functions. Sum over state this where EI is the energy of the ith state of the system. Summation is carried out over all state. In our case, K this equation where ZAC, ZA, ZB are the partition function for the activated complex and the reactant AB respectively for the translational motion of a particle. The set of states continue the partition function is replaced by an integral which is equal to this. You can see this equation where h is Planck constant and m is the mass of the particles. We assume that volume occupied by the particle to be equal to this is the partition function with respect to the three translation degree of freedom. But as the system has only 1 degree of freedom along the direction of reaction, we obtain this where ZAC is the partition function for the activation complex over all degree freedom except the translation degree of freedom. Equation 6.8, 6.10 and 6.12 we obtain this. Uh, you can see this equation. The conditional length delta is reduced. The statistical equations are directly associated with thermodynamics quantity. We have this equation and hence uh, our result is here. G is the excess free energy of the activated complex as compared with the total free energy of the reactants, i.e. the free energy of activation. In the derivation of expression 6.15 is it is assumed that the system having reached the activation barrier is necessarily made to undergo a chemical transformation. This may not take place. However, introducing an additional factor, the transmission coefficient, yes, we obtained the final expression for the rate constant of a homogeneous gaseous reaction, the Eyring formula. This is Eyring formula, where S is the entropy of activation and H is the enthalpy of activation. The volume of X equal to 1 corresponds to an adiabatic reactions, i.e. to proceed in which the parameter of the mechanical system change slowly. In chemical reactions, such parameters are the position of atomic nuclei. With each of the configuration of the nuclei, the electron move as through the nuclei remain fixed. The process is non-adiabatic. X is less than 1 and may assume volume of the order of 10 to the power minus 15 unity. These reactions proceed adiabatically. The X value observed in gas phase reaction are mostly close to unity. These reactions proceed adiabatically. The factor Kt per half at ordinary temperature is of the order of 10 raised to power 13 second per minute. Let us compare to Eyring formula with the Ernst formula. If the enthalpy of the activation is identified with the activation and entropy, the pre-exponential term will be given by this equation. The value of the activation parameter are determined from the temperature dependence of K constant. At x is equal to 1, we have this equation. The second term depend but slightly on t and may therefore be neglected. We obtain the linear dependence of this from the slope of the straight line. We have h positive. The value of h positive is found from the ordinate intercept. The non-linearity of the dependence of this is indicated of the complexity for the process. I it so that the process become cooperative. In such a process, the free energy of the activation is not constant and depend on the number of systems that have reacted and hence on T. Suppose we are riding in an overcrowded bus and it is time of us for us to get off. It is difficult to do so. A large energy of activation is required. As the number of people that have left the bus increase, this energy diminished. This is spectral examination of cooperative kinetics. Calculation of rate constant of formula can be carried out only for the simplest gas phase reactions. It should be emphasized that HKT must not be related as the lifetime of the activated complex because it leads to contraindications. Statically, equilibrium cannot be set up in 10 raised to power minus 13 and minus 10 raised to power minus 14 second. The lifetime of the system in the state corresponding to wall of reaction coordinate from this is equal actually proportional to lambda, so delta. This time must be treated in the same way as the lifetime of state dealt with in the Maxwell-Boltzmann theory. From the smallness of this, one cannot calculate that the equilibrium between the activation complex and the reactant cannot be stabilized. The term activated complex refer to state of an atomic system that undergo transformation and does not imply the existence of the metastable complex, which can be studied by chemical and physical method. The airing theory is applicable to gas phase chemical reaction and also be to physical kinetic process. This theory cannot so be used in dealing with the reaction taking place in solutions. Let us now turn to catalysis. As has already been said, the role of a catalyst is lower the free energy of activation and hence to increase the rate constant of the reactions. Two types of catalysis are distinguished: heterogeneous and homogeneous. The first case, the catalyst forms a separate phase and the reaction takes place in at interface between the phase. The process being the adsorption of the reactant at this interface. Say on the surface of a solid, catalyze which speed up the reaction in a gas or a liquid. The absorption is accompanied by a change in the electric structure of the reactants and by a decrease in free energy of activations. After this, after the reaction has gone to completion, the product are di- dissolved from surface. In homogeneous catalysis, the catalyst and the reactant are in a single phase, say in a solution. The catalyst form an intermediate complex with the reactant, which is then decomposed into the catalyst and the reaction product. Enzyme function either in solution or in supermolecule structure. The sorption of the reactant called substrate and the reaction take place on the some part of the surface of a large protein molecules. In this sense, enzyme catalysis is similar to heterogeneous catalysis, but the protein enzyme and the small molecule of the substrate are present in one phase in solution. There is a strict sto- there is a strict stoichiometry of the interaction. As a rule, one protein global interact with one molecule of the substrate or another ligands. The interaction lead to formation of an enzyme substrate complex. Whole structure and property are studied by physical and chemical method. Enzyme catalysis in solution in is a homogeneous catalysis. We may regard an enzyme as a base black box that transformation transforms the input signal, the substrate molecules, to the output signal, the product molecules. There are two methods of investigation are arranged and operation mechanics of black box, the study of the molecular structure of the enzyme and enzyme substrate complex, and the study of the kinetics of enzyme reactions. Thank you.